We're going to get started again with some more problems to prepare for our final exam in Engineering 110. So we're on to question 3. Again, kind of dealing with stress states and basically working with the Wheatstone bridge configurations. And in this problem, kind of the calibration and shunting. So question 3, elastomeric self-healing materials. So we created this, basically, and this is kind of a real example. I can't remember where this was done, what research, but I could find it if I was interested. Basically, they've created this new material, has some really interesting kind of properties. It's placed under this biaxial stress state. So let's kind of write out our coordinate system. So I'm going to say this is 1, this is 2. So there's some stress in the 1-1 direction. There's some stress in the 2-2 direction. So my stress state is going to be, there's nothing else kind of written here. So sigma 1-1, sigma 2-2, 0, 0, 0, 0, 0, 0, 0. My strain state, or my strain tensor, is going to be strain in the 1-1, excuse me, 1-1, 0, 0, strain in the 2-2, or 0, 2-2, and there will also be some strain in the 3-3. But we place our strain gauge basically in 2 dimensions, so we're not going to even work with this one. So let's continue reading below. And actually, if we want, we could actually start to kind of write out. So the strain in R1. So again, our 1 strain gauge, we're always looking where is the wires expanding. It's going to be equivalent to, it's going to expand in the 1-1 direction. The strain in the 4-4, that's going to be given by our strain in the 2-2 direction. If we write out kind of the full, basically strain values here, which is just going to be, excuse me, undo that, one more undo. There we go. 1 over E times sigma 1-1 minus nu sigma 2-2. And strain in 2-2 is going to be 1 over E times sigma 2-2 minus nu sigma. So let's go ahead down. Mechanical properties of materials investigated, bridge configuration below. So the stress applied along the length of the material. So the length, the long direction here is 1 kilopascal. So sigma 1-1 is 1 times 10 to the 3 pascals. We do not know the Young's modulus of the material is 10 megapascals. So E is equal to 10 times 10 to the 6 pascals. We know our nu is 0.4. This is elastomeric material, polymer, essentially a polymer right here. Gauge factor is 1, so F equals 1. The resistance of our strain gauges are all equal and 100 ohms. So right here, F is equal to 1. Our resistance to our strain gauge is equal to 100 ohms. Our shunt resistor, so if we remember, draw our configuration, 2, 3, 4. So we have a strain gauge here, we have a strain gauge here, we have nothing happening in here or here. And now we attach, basically, remember that switch, that RS, the shunt, to it as well. And in that shunt equation, remember, we had an equivalent strain. So let me put this out. Strain equivalent was equal to minus 1 over F times delta R over R. That was equivalent to, in this example, 1 over F RG over RS plus RG. So, we know our RG, our RS, shunt resistor is 300 times 10 to the 3rd ohms. So we know this, we know this, we know this, and we know that factor, so we can calculate that equivalent strain when we need to. So when we place it across the first line of the bridge, we initially read a value of 1 from our old oscilloscope. Once the stress is applied, the oscilloscope reads a value of 5. The material is placed at from room temperature to internal temperatures of 37°C. One things we forgot to mention here is the thermal strain. And the thermal strain is equivalent to alpha times delta T. And alpha here, the linear thermal expansion coefficient, is this value right here. So we need to now solve for all the stresses and strains in the strain gauges, and then muscle cells will exhibit a yield stress of 0.4 megapascals and yield at maximum normal stresses. Will this material yield in their stress state? So let's go ahead and figure out all of these unknowns. So we can calculate, and I am going to, one of the other things we want to write out, we wrote this expression for the equivalent strain when we close our switch for our shunt. We could also write out an equation for total strain. So our total strain is going to be, because initially we read this value, when we shut our switch, we read a value of 1 on our oscilloscope. But when we start to kind of apply our stresses, we read a value of 5. So the total strain is going to be this strain once we flip their switch times 5 over 1. It's just kind of the ratio there. And remember, that is equal to also sigma 1 minus sigma 2 minus sigma 3 plus sigma 4, where these two are 0 because we don't have those on our screen. So let's go ahead and pull Mathematica up, start to play around and see what's happening with our material. So let's go ahead and define some values. So I know that sigma 1 is equal to 1 times 10 to the third. I know that my nu is equal to 0.4. I know that my E is 10 megapascals, 10 to the sixth. I know my F is equal to 1. I know my, let's scroll down here. I know my RG is equal to 100. I know my RS is equal to 300 times 10 to the third. I know that my F is equal to 1. My delta T is equal to 37 minus 25. So, because we're raising temperature, so the change in temperature. Or my alpha, my linear thermal expansion coefficient, is equal to 10 to the minus 5. And let's see, do we have anything else? Let's start off with this. I also know that my E equivalent, my EE, oops, what's going on here? We never want to use E, we want to use Y. My EE is going to be equal to minus 1. It's 1 divided by F times RG divided by RG plus RS. So, and I want to take the absolute value of that, and I know that my total strain is going to be 5 times E. So, we're moving along pretty nicely right here. So, let's also kind of define what else we have in this equation. So, I'm going to say that my stress, we actually know the stress tensor up there. So, let's go ahead and look here. So now we have got that E1 equals E11 plus ET. And then we know that E4 equals E22 plus ET. Got those. ET is equal to alpha times delta T. There we go. We also know that E11 is equal to 1 divided by Y times sig11 minus nu times sig22. And we know that E22 equals 1 divided by Y times sig22 minus nu times sig11. So let's go ahead and let's take a look inside E11, E22. So we have an expression that gives us our total strain. So we know that our total strain is this value, but we also know that total strain is equal to E1 plus E4, which is this value. So everything here is just left in terms of sig22. So we wanted to figure out, find all the stresses and strains associated with the strain gauge. So all I'm going to do is solve. Total strain, set it equal to this. I'm going to solve for sig22. And voila. So sig22 equals this. We've got that. So what about sigma11? We know that. What about E11? We know that. E22? We have that. We're good. Now, it says muscle cells will exhibit a yield stress of 0.4 megapascals and will yield typically at maximum normal stresses. So we're already in our principal normal stress state, which CH is larger, sigma 1 and sigma 2. So this is 22,000 pascals. That is much lower than that. So 4 times 10 to the 5th pascals. Actually, let's show that. So let's look at 4 times, or 0.4 times 10 to the 6. 400,000, so we are well below it, so this material will not yield. So that's it. That's pretty straightforward how you can solve these problems. So hope that made sense. If you have any questions, please let me know. And we're on to our last problem in this practice exam. Thanks. Have a good one. Bye.